On the evening of July 17th, 1981, about 2,000 people were dancing in the atrium of a brand new luxury hotel in Kansas City. The Hyatt Regency had a lobby that was, by the standards of the time, breathtaking. A soaring, glass-roofed space 4 stories tall with 3 walkways suspended in the open air above the dance floor, one stacked above the other, hanging from the ceiling on slender steel rods. People stood on those walkways to watch the party below. They were beautiful. They were a year old. And at about 7 o'clock that evening, 2 of them, one hanging directly above the other, tore loose from the ceiling and fell, fully loaded with people, onto the crowd in the atrium. 114 people died. More than 200 were injured. It remained for 40 years the deadliest structural collapse in the history of the United States. And here is the part that has haunted engineers ever since. The walkways did not fall because of a strange new force, or a freak event, or bad steel. They fell because of a small change to a connection detail, a change that doubled the load on a single set of parts, and that, on the drawings, looked like almost nothing at all. This is the story of the 2 words that killed 114 people. To understand what happened in Kansas City, you have to start with the building itself, and with an idea that was, in 1980, considered modern and elegant. The Hyatt Regency Kansas City opened in July of that year. Its centerpiece was the atrium, a grand interior courtyard with a glass roof, surrounded on all sides by the hotel's rooms and balconies. To let guests move between the 2 main wings of the hotel without going all the way down to the ground floor, the architects suspended 3 walkways across the open space of the atrium, one on the 2nd floor, one on the 3rd, one on the 4th. And here is the design choice that defines the whole story. The 2nd floor walkway and the 4th floor walkway were not side by side. They were stacked. The 4th floor walkway hung in the air directly above the 2nd floor walkway, with the 3rd floor walkway offset slightly to one side. Now, a suspended walkway is a genuinely clever piece of engineering. Instead of resting on columns that rise from the floor, columns that would clutter the atrium and ruin the open space, the walkway hangs from the roof. Steel rods drop down from the ceiling structure, and the walkway is fastened to those rods. The weight of the walkway, and everyone on it, is carried up the rods, into the roof, and out to the building's main structure. The atrium floor stays completely open. It looks like the walkways are floating. But that elegance comes with a hard requirement. Every connection in that hanging chain, every point where a rod meets a walkway, every point where a rod meets the ceiling, is now carrying real, heavy, gravitational load. There is no backup. There are no columns underneath to catch the walkway if a connection lets go. In a suspended structure, the connections are not details. The connections are the building. So here is how the walkways were originally designed. And pay close attention because the entire disaster lives in the difference between this design and the one that got built. In the original drawings, the 4th floor walkway and the 2nd floor walkway, the 2 stacked ones, were to hang from the same set of long steel rods. Picture a single rod hanging from the ceiling, running all the way down. The 4th floor walkway would be fastened to that rod somewhere in the middle. And then the same rod would continue downward past the 4th floor walkway all the way down to the 2nd floor walkway, which would be fastened to the bottom end of it. 1 continuous rod, 2 walkways. The rod hangs from the ceiling, the upper walkway clamps onto the rod's middle, the lower walkway clamps onto the rod's end. Hold that picture in your mind. one long rod carrying two walkways, the upper one in the middle and the lower one at the bottom. That design had a problem. We will get to it, but it was not the design that killed anyone. What killed people was the fix. The original single rod design had a flaw, and it was not a flaw of strength. It was a flaw of construction. Think about what that long, continuous rod actually requires. The fourth floor walkway has to clamp onto the middle of the rod. But to get a nut onto the middle of a rod, you have to thread that nut all the way up from the bottom end of the rod, turning it, by hand, up the entire lower length of the rod until it reaches the middle. The whole bottom portion of the rod, the part below the fourth floor connection, would have to be threaded, cut with screw threads along its entire length, just so the nut could travel up it. That is slow, it is expensive, and a threaded rod is weaker than a smooth one because the threads cut notches into the steel. So the steel fabricator, the company that actually made the parts, looked at that detail and proposed a change. And the change seemed, at the time, like nothing more than a practical simplification. Here is the change. Instead of one long rod carrying both walkways, the fabricator proposed two shorter rods. One rod would hang from the ceiling down to the fourth floor walkway and stop there. Then a second, separate rod would hang from the fourth floor walkway down to the second floor walkway. The rods no longer ran continuously. The upper rod ended at the fourth floor walkway, the lower rod began at the fourth floor walkway. On the drawings, this looked almost identical to the original. Same walkways, same heights, same rods of the same thickness. The only difference was that the rod was now in two pieces, broken at the fourth floor connection, instead of one piece passing through it. The change was submitted, it was reviewed, it was approved. And it more than doubled the load on the connection at the fourth floor walkway. Nobody in the approval chain caught it. Not the fabricator who proposed it, not the engineering firm that stamped it. The whole disaster is in that one missed doubling. Now, you are probably thinking, how can simply cutting a rod in two double a load? The walkways did not get heavier. The people did not get heavier. That is the exact question this whole episode exists to answer. And the answer is one of the cleanest, most teachable ideas in all of structural engineering. It is the idea of a load path. A load path is the route that a force takes through a structure on its way to the ground. Every ounce of weight in a building has to get to the earth somehow. It travels from where it sits, through beams, through connections, through columns or rods, down into the foundations. And here is the thing. When you change the geometry of a structure, even slightly, you can change that route. You can change which parts carry the load and how much. The Hyatt walkways did not get heavier. The load path got rearranged, and one connection ended up standing under twice the weight it was ever meant to hold. To see exactly how the load doubled, we have to zoom in on the connection itself, the place where a rod met a walkway. The walkways were not held up by being tied to a rod with a knot. They were held up by something more specific. Each walkway was framed by long horizontal steel members called box beams. A box beam is exactly what it sounds like, a beam with a hollow rectangular cross-section, like a long metal tube. The walkway's concrete floor sat on these box beams. At the points where a suspension rod came down to a walkway, the rod passed through a hole in the box beam. And underneath the box beam, a large nut was threaded onto the rod. The nut pressed up against a washer, The washer pressed up against the underside of the box beam, and that is what held the walkway in the air. The entire weight of the walkway and everyone on it pressed down on that box beam, and the box beam pressed down on the nut, and the nut held the rod, and the rod carried it all up to the ceiling. So the critical question at every connection is simple. How much load is squeezing on that one nut and that one box beam? Now let us do the comparison, and this is the heart of it. In the original design, the single continuous rod, think about the fourth floor box beam. The rod passes through it, and a nut under that box beam holds the fourth floor walkway. What load does that nut carry? It carries only the weight of the fourth floor walkway, just that one walkway. Because the second floor walkway, hanging below, is supported by the bottom end of the same rod. The second floor walkway's weight is carried by the rod itself in tension, down past the fourth floor connection. It pulls on the rod, not on the fourth floor box beam. So in the original design, the fourth floor nut holds one walkway. The ceiling holds both. The load is shared sensibly. One walkway of weight on the fourth floor connection. That is what it was designed for. That is what the box beam and the nut were sized for. Now the as-built design. The rod is in two pieces. The upper rod comes down from the ceiling and ends at the fourth floor box beam held by a nut. The lower rod begins at that same fourth floor box beam held by another nut and runs down to the second floor walkway. So follow the load. The second floor walkway's weight pulls down on the lower rod. The lower rod is attached to what? The fourth floor box beam. The lower rod hangs the entire second floor walkway off the fourth floor box beam. And the fourth floor box beam is also still carrying its own walkway, the fourth floor walkway. So now that one box beam and the nut on the upper rod above it are carrying two walkways. The fourth floor walkway resting on the beam, plus the second floor walkway hanging from the beam. The connection that was designed to hold one walkway was now being asked to hold two. The load on it had exactly doubled. So the load on the fourth floor connection doubled. But you might still be thinking, so what? Engineers build in safety margins. Maybe the connection could take double the load anyway. It could not. And to understand why, we have to look very carefully at how that box beam was actually built, because the box beam had a hidden weakness that the doubled load found instantly. Remember, the box beam is a hollow rectangular tube, but it was not extruded as a single seamless piece. It was fabricated by taking two C-shaped steel channels and welding them together along their length, back to back, to form the closed box. The weld ran along the top of the beam, and the suspension rod passed down through a hole drilled near that welded seam. The nut and washer pressed up against the bottom of the box, but the load then had to travel through the walls of the box up to where the rod's hole was, and the geometry of that load path ran straight at the weld. Here is the mechanism that failed, and it is a beautiful, terrible piece of structural reasoning. The nut and washer under the box beam push up. They concentrate all of the walkway's load onto a small patch of the bottom of the beam right around the rod. That load has to spread out through the beam and up into the rod's hole. But the washer is small. The force is concentrated. And a concentrated force pushing on the bottom of a welded box wants to do something specific. It wants to push the bottom of the box up and pry the box open at the weld. the load was effectively trying to peel the two welded channels apart. The connection's strength, in the end, came down to the strength of that weld and the small amount of steel around the rod hole resisting being torn through. Under one walkway's worth of load, that was barely adequate. The original design was not generous, but it held. Under two walkways worth of load, the steel around the hole simply did not have enough material to carry it. The connection was being asked to do something the metal there could not do. Now let us put real numbers on this, because the numbers are the whole point of this channel. When investigators from the National Bureau of Standards examined the collapse afterward, they did the calculation that, by rights, should have been done before anyone walked on those walkways. The connection as it was actually built, the box beam, the weld, the washer, the doubled load from the as-built two-rod design, could carry, according to the investigation, only around 30% of the load that a properly designed connection should have been able to support under the building code of the time. 30%. But it gets sharper than that. Even the original single rod design, the one that was never built, the investigators found that connection too would only have met roughly 60% of the code requirement. So sit with that. The original design was already under strength. It would not have passed a careful check. And then the as-built change took an already deficient connection and cut its capacity roughly in half again. The walkways, on the night they fell, were standing on a connection working at something like a third of the strength the law required. So let us actually write down the equation, or rather the simple, unforgiving piece of arithmetic, that killed the people in that atrium. At its heart, this is not advanced mathematics. It is the most basic statement in all of structural engineering, and it is almost insultingly simple. It is this: a structure stands if and only if the demand is less than the capacity. Demand, the load actually placed on a part. Capacity, the load that part can actually carry. As long as demand stays below capacity, the part holds. The moment demand exceeds capacity, the part fails. Demand less than capacity. That is the entire equation of whether a building stands up. Everything else in structural engineering is just a method for calculating those two numbers honestly. Now watch what the as-built change did to the two sides of that equation. Start with the capacity side. The capacity of the fourth floor connection, the box beam, the weld, the steel around the rod hole, was a fixed property of how the connection was built. The two-rod change did not improve the capacity. It used the same box beam, the same kind of weld. The capacity stayed roughly where it was, already deficient, around 60% of code in the original, and the new geometry's particular load pattern dragged the effective capacity even lower. So the capacity side of the equation was small, and the change made it no better. Now the demand side. In the original design, the demand on the fourth floor connection was one walkway's weight. In the as-built design, the demand on that same connection was two walkways' weight. The change did not touch capacity. It doubled demand. It took the demand term and multiplied it by 2, while leaving the capacity term sitting where it already was. And that pushed demand straight past capacity. Now let us be precise about the demand, because there is a second, crueler layer to it. The demand on a walkway is not just the steel and concrete. It is also the people. Engineers call the weight of the structure itself the dead load. It never changes. They call the weight of the people and furniture the live load. It varies. The total demand is dead load plus live load. On a normal day, a walkway might have a few people strolling across it. The live load is light. But on the evening of July 17, 1981, the Hyatt was holding a tea dance, a popular weekly event, and people had crowded onto the walkways to watch the dancing in the atrium below. The walkways were not just carrying their own weight, they were packed with standing spectators. The live load was near its peak. So the demand side of the equation reached its maximum. A doubled structural load path, fully loaded with a crowd, on exactly the night the equation was finally tested. The fourth floor connection was carrying the worst case it would ever see. So here is the full equation that killed 114 people. The demand on the fourth floor connection was the dead load of 2 walkways, plus the live load of a crowd packed onto both of them. The capacity of that connection was the strength of 1 welded box beam and the steel around 1 drilled hole, a capacity that was already below code and that the as-built geometry made worse. On the night of the tea dance, demand climbed, and capacity sat where it had always sat, and the 2 numbers crossed. Demand exceeded capacity. And when demand exceeds capacity in a structure with no backup load path, no columns underneath, no second route for the force to take, there is no warning and no second chance. The connection lets go, and everything it was holding falls. The strange equation of the Hyatt Regency is the simplest one this channel will ever show you. Demand less than capacity. The walkways were elegant and beautiful, and they violated it. So let us go back to the atrium on the evening of July 17th, 1981, with the equation in hand. The fourth floor walkway and the second floor walkway are both crowded with spectators. The third floor walkway, offset to the side, is also full. The dance floor below is packed. The demand on the fourth floor connection has been climbing all evening as more people stepped onto the walkways, and at around 7 o'clock, it crosses the capacity. The steel around the rod hole in the fourth floor box beam begins to fail. The load was trying to pull the rod and nut straight through the end of the box. And once that steel started to tear, it did not stop, because there was nothing to stop it. As the steel deformed, the connection got weaker, which meant it carried less, which dumped its load onto nothing. There was no other path. The connection simply pulled apart. When the fourth floor connection let go, the upper rod pulled free and the fourth floor walkway dropped. But remember the geometry. The second floor walkway was hanging from the fourth floor walkway. So when the fourth floor walkway fell, it did not just fall by itself. It fell onto the second floor walkway directly below it, and the 2 of them, both fully loaded with people, came down together as a single catastrophic mass onto the crowded dance floor of the atrium. The third floor walkway, on its separate offset supports, stayed up. Witnesses described it as instantaneous, a loud crack, and then the walkways were simply gone from the air and on the floor. The entire collapse, from the first failure to the walkways striking the ground, took roughly the length of time it has taken me to say this sentence. There was no time to run. There was no time to do anything at all. 114 people were killed. More than 200 were injured. The dead were on the walkways and on the dance floor beneath them. The rescue effort lasted through the night. Heavy equipment had to be brought into the hotel lobby itself. It was, at the time, the deadliest structural collapse in the history of the United States, and it would hold that grim record for 40 years. And from the very first hours, the question that engineers and investigators asked was not the question the public expected. They did not ask whether the steel was bad, or whether there had been an earthquake, or whether the building had been overloaded beyond any reasonable use. They asked a much quieter and much more disturbing question. How did a connection this far below code get designed, get reviewed, get approved, and get built? And how did the people responsible for checking it never run the simple arithmetic that would have caught it? The investigation into the Hyatt Regency collapse became one of the most consequential in the history of engineering. The National Bureau of Standards conducted the technical analysis, and what they found was, in a way, worse than a single villain. They found a chain of failures of responsibility, no single link of which was a dramatic act of malice. The structural engineering firm had produced the original design, the single rod design, and that design was itself already deficient, already below code, as we have seen. Then, the steel fabricator, finding the original rod detail awkward to build, proposed the two-rod change. The change request was communicated, reviewed, and the engineering firm's seal was applied to the revised drawings. But the calculation that should have accompanied that review, the simple recheck of demand against capacity at the modified connection, was, by the investigation's account, never properly performed. The doubling of the load was never caught, because at no point did the right person sit down and do the arithmetic on the connection as it was actually going to be built. There is a detail in this story that engineers find almost unbearable because it is so close to a save. More than a year before the collapse, during the construction of the hotel in October 1979, a section of the atrium roof had collapsed. That earlier collapse was investigated, the roof was repaired, and the building was completed. But that roof collapse should have been a screaming signal that the connections and the structural review process on this building deserved a deep, skeptical, independent look. The warning was there. A piece of the building had already fallen down once before it ever opened. And the walkways, hanging in the same atrium, under the same engineering oversight, were not given the fresh, ground-up structural recheck that the earlier failure should have demanded. The signature of this disaster is not a single bad calculation. It is a system in which the responsibility for one specific check, does the connection as built carry the load, belonged, in the end, to no one clearly enough that anyone actually did it. What the Hyatt Regency collapse changed. It changed permanently. The disaster led directly to a fundamental rethinking of the responsibilities of the structural engineer of record, the engineer whose seal goes on the drawings. After Kansas City, the engineering profession in the United States moved decisively toward the principle that the engineer of record bears clear, non-delegable responsibility for the structural adequacy of the connections, not just the major members, and that shop drawing changes proposed by fabricators must be genuinely engineered, not merely glanced at and stamped. The case became a permanent fixture of engineering ethics education. Almost every engineer trained in the decades since has studied the Hyatt Regency walkways, not primarily as a problem of steel, but as a problem of responsibility, communication, and the discipline of the check. The two engineers who had sealed the drawings lost their professional licenses in Missouri. The technical lesson and the ethical lesson in this case are the same lesson. An equation that nobody is clearly assigned to compute is an equation that does not get computed. The Hyatt Regency walkway collapse is now, in engineering education worldwide, one of the most heavily taught case studies that exists. It is taught in structural engineering courses as the canonical example of how a connection, not a beam, not a column, but a connection, can be the weakest and most overlooked element in a structure. It is taught in engineering ethics courses as the defining case of the engineer of record's duty of care. It is taught in project management and communication courses as a study of what happens when a design change crosses between two organizations, the engineer and the fabricator, and the responsibility for re-verifying that change falls into the gap between them. All of those readings are true. But here is the thing about this disaster that I find most haunting. And it is the thing that connects it to every other story on this channel. There was no missing science. When the Tacoma Narrows Bridge fell, the equation of flutter genuinely lived in another field. The bridge engineers did not have it. But the equation that would have saved the Hyatt Regency walkways was not in another field. It was not advanced. It was not new. It was demand less than capacity. The first thing any structural engineer ever learns, the arithmetic of a connection. A calculation a competent engineer could complete in an afternoon. The mathematics was not missing. The mathematics was sitting right there, fully known, completely standard. What was missing was the act of doing it. On the right detail, at the right time, by a person who clearly understood that doing it was their job. The equation existed. The discipline of running it did not. I want to leave you with the thought that I find most sobering about the Hyatt Regency, and it is the reason this story belongs on this channel. We tend to imagine that engineering disasters come from the frontier, from the new, the untested, the things at the edge of what is known. And sometimes they do. But the walkways did not fall at the frontier. They fell at the center. They fell on the most basic, most well-understood, most thoroughly settled equation in the entire discipline. Demand less than capacity. A statement so simple it can be written in 4 words and understood by anyone. And 114 people died because somewhere in a chain of busy, credentialed, well-intentioned professionals, that 4-word equation was never actually evaluated for the connection that mattered. The terrifying lesson of the Hyatt Regency is not that engineering is hard. It is that the hardest part of engineering is not the mathematics. It is the discipline of making absolutely certain that the simple, known, mandatory calculation actually gets done on the real thing as it will really be built by a person who knows the answer is theirs to find. That discipline had to be enforced, in the United States, by tragedy. The responsibilities of the engineer of record were sharpened. The review of fabricator changes was tightened, and the case entered every ethics syllabus in the country, all of it written, in a real sense, in the aftermath of one atrium. The walkways were elegant. The arithmetic that condemned them was trivial. The gap between those two facts is the whole story. Strange equations are not always strange because they are difficult. Sometimes they are strange because they are so simple that everyone assumes someone else has already checked them. The load does not care who was supposed to check. When the crowd steps onto the walkway, the equation runs, and it returns the same answer it would have returned on the drawing board a year earlier to anyone who had bothered to look. If you enjoyed this one, the story of how a single skywalk in another city was quietly checked, found dangerously flawed by a curious student's question, and secretly reinforced over a series of nights while the public never knew, the Citicorp Center in New York is a story for another day. Strange Equations is here for the math behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.